Welcome to another video on our EmbeddedCraft channel. In this video tutorial we are talking about using SPI in Linux. We will start with Introduction to SPI. And next we will demonstrate working on MAX7219 Serial Interface LED driver. We will demonstrate character display on LED matrix. And later we will write C code for MAX7219 chip. So relaxed and watch this video till the end. You will be requiring a single board computer running Linux. One important point, board should have SPI interface. We are using Raspberry Pi version 4 board. You can choose any version of board. We also need a LED display module. We are using a generic module having MAX7219 connected to LED matrix module. And some connecting cables and Ethernet cables. You can refer these two videos. In this video we are showing using GPIO pin in Linux. And in this second video, you will learn using I2C devices in Linux. Link to the both videos is given in the description. SPI is Serial Peripheral Interface Protocol. SPI interface involve 3 or 2 wires. 3-wire interface is faster than 2-wire interface. SPI is a master-slave configuration. Master device will start communication, and provide clock to slave device. Data is transferred on each clock. Data can travel in both direction. That means from master to slave and slave to master. SPI device speed can be up to 60 megabits per second. Now the question may be where SPI interface is used. Many sensors chips are having SPI interface. For example, thermal monitoring and pressure monitoring systems. And SPI is also used in NOR flash interface. Let us talk about SPI interface lines. There are 4 lines. This is SCLK clock line. Clock is generated by SPI master. SCLK line is output line from master. For data transfer there will be 2 lines. One is MUSI. MUSI is master out and slave input. Data is sent from master to slave. This second data line is MISO. That is master in and slave out. Means, data will be transferred from slave to master. And there will be a chip select line. We need to enable chip select line to select SPI slave device. Chip select line is generally active low. There are 2 configurations. Number 1, independent configuration. And number 2, daisy chain configuration. These configurations depend on how the chip select line is wired. Let us focus on independent configuration. You see the chip select line of each SPI device is wired independently. And data lines common to all SPI devices. We will able to use multiple devices on same SPI interface. You can connect multiple sensors to the same SPI interface. Let us move to the second configuration. This is daisy chain configuration. Chip select is common. Output of one SPI device will be input to the next SPI device. MISO line of one SPI is connected to MUSI line of next SPI device. This will enable one SPI device to send data to the next SPI device. All SPI devices together will form a big shift register. Scroll message display is the example of daisy chain configuration. Let us see how to access SPI device in Linux. In Linux IOCTL system call is used. Help on this system call is available in Linux man pages. Basically you need to open SPI device, using OpenCall. Pass handle to IOCTL system call. Then provide data for SPI device. Data need to be given in the form of structure. And that structure pointer is this arg argument. Interpretation of that data will depend on this request argument. We will see exact usage of IOCTL system call in, next slide. Accessing SPI device is 3-step process. Step number 1 is open SPI device. Step number 2 is configuring of SPI device. Step number 3 is reading and writing to SPI device. Let us see these steps in detail. Let us consider that SPI device is connected to SPI 0 interface. First step is to open SPI 0 device. So, we will say, open, and root, and dev, and SPI 0. And second argument is access flag. O_RDWR means, we want to open SPI device read-write mode. This open call will return handle to SPI device. Next step is to configure SPI device. Configuring means, for example, setting of SPI data transfer speed. And this is going to be done by IOCTL system call. The first argument is the SPI device handle. Second argument is the command. Because we need to set SPI data transfer speed. So the command will be SPI IOC WR max speed HZ. So, first argument will be F_SPI. And the second argument is the command. Third argument is SPI frequency, which is 2 MHz. There are many configuration commands for different settings of SPI device. For reading and writing to SPI devices, we have to use a predefined SPI IOC transfer structure. This structure is defined in SPI dev.h file. As you can see, we have transfer buffer and receive buffer elements in the structure. This is the length of data we want to transfer. And here is the speed of SPI device. Let us consider a practical situation. Suppose, if we want to write 0 to 0xa register of SPI device, we need to prepare our 16-bit strings. str_temp0 will get 0x0a, and str_temp1 will get 0x00. We will fill SPI IOC transfer structure. TX buffer will point to str_temp string. Length will be 2, because we are sending 2 bytes. RX buffer will not point to anything, as we are not going to receive any data. Finally, we will use IOCTL system call. We will use SPI IOC message request and pass our structure. This will send 2 bytes to the SPI device. And SPI device will interpret 16 bytes. Interpretation is that, first byte which is 0A is the register. And the second byte is the data which is 0. And if we want to read, from SPI device, simply read from, RX buffer element of SPI IOC, transfer structure. For exact information about SPI device, read datasheet. For example, to understand interpretation of 16 bits, refer datasheet of MAX7219 chip. With this we are concluding our first part of SPI interfacing video. Stay tuned for the second and last part of this tutorial.
Visit our website for more articles and tutorials. Visit us at www.embeddedcraft.org.
In this video tutorial we are talking about MAX7219 LED display controller. This is the second part of our video, SPI in Linux. You can watch the first part of that tutorial, link is given in description. In this tutorial, we will start with introduction to MAX7219 IC. And, next we will show configuration of MAX7219 LED controller. So, relax and watch this video till the end. We will use MAX7219 SPI Interfaced LED Display Driver IC. MAX7219 is serial interfaced, 8-digit, LED display driver. It has 4-line serial interface. D in is Muzzy line. D out is MISO line. Load is chip select line. And here is the clock line. MAX7219 works in BCD decoding mode. And also in no decoding mode. MAX7219 can drive 7-segment LED display. And also 8x8 LED matrix. Basically it can drive 64 LEDs individually. We will use it to drive LED matrix. MAX7219 will able to drive 8x8 LED matrix. In generic module, we have LED matrix and MAX7219 IC. Let us see how LED matrix works. LEDs are organized into 8 columns and 8 rows. LEDs connected at intersection of each row and column. Here are pin numbered from 1 to 8 and 9 to 16. One big point is how to identify pin number. We need to search name or half moon symbol. You will able to find name of module or half moon symbol. Pin numbers will be from left to right. Leftmost pin is pin number 1, 2, 3 and so on. Connection of MAX7219 with Raspberry Pi 4 board is straightforward. MAX7219 has DIN pin, which is basically master out slave in pin. DIN pin is connected to Muzzy pin of Raspberry Pi board. Muzzy is pin 19. Clock pin of MAX7219 is connected to SCLK of Raspberry Pi. Load pin of MAX7219 is connected to PO number 25. Load pin can be connected to any PO pin of Raspberry Pi. We will see role of load pin shortly. Ground pin of MAX7219 is connected to ground pin of Raspberry Pi. And most important connection is rows and columns. D0 to D7 pins of MAX7219 are connected to column of LED matrix display. Segment pins of MAX7219 are connected to rows of LED matrix. As we will use LED matrix module, so you will find all connections already present. You can identify pins on LED matrix module. MAX7219 has various registers. These are the segment drivers pins, Seg A to Seg G, and DP line. Here we have digit drivers. It has DIG0 to DIG7 lines. It has registers to control functionality of LED drivers. For example, shutdown register to turn LED driver on or off. Same way we have intensity control registers. Scan limit register, decide how many digits are going to be displayed. Every register has 4 bits address. But data to SPI is transferred in 16 bits format. First 8 bits, D7 to D0 will represent data, which we want to write into a register. D11 to D8 will represent address of register. D15 to D12 are don't care bits. These bits can be considered as 0. Let us see how address is created. Register address is of 4 bits. If we consider don't care bits to 0, in this case, decode mode register address will be 0x09. Scan limit register address will be 0x0b. Suppose we need to write 7 in scan limit register. First step is to find out address of scan limit register. As per this table, you can see, address of scan limit register is B. In that case 16 bits which we need to send is 0B, 07. 0x0b is address of register, and 0x07 is the value, which will be written in scan limit register. To write 16 bits to SPI device, we need to follow these steps. First make load line 0. And then data is sent on each clock. MSB is send first and LSB is send at the end. Bit order is configurable in Linux SPI driver. Let us plan display of character A. We will glow LED in such a way that it resembles character A. Because this LED matrix is a common cathode type, writing 1 will glow LED. So, in this way, you can see, value for first row, should be 0x70. And in value for second row, will be 0x88. And value for third and fourth row, will be 0x88. Fifth row will be 0xF8. Now, we have values for each rows, to display character A. If we want to display character A on LED display, we need to write 70 into digit register 0, 88 into digit register 1, and so on. In this way, we can create fonts. Same way, we will able to write character B. We need to write FC into data register 0, 0x42 into data register 1, and so on. We have figured out values need to be written in data register. Now we are ready to write C code. We need to write code in 3 steps. First step is to initialize SPI Device 0, because MAX7219 is connected to SPI 0. Second step will be preparing LED controller. And finally, display character. First we will open SPI Device. Set SPI mode. Set SPI speed to 2 meg. Prepare SPI IOC transfer structure. Initialize GPIO pin, to make load pin low. Send data using IOCTL system call. Make GPIO pin high, to disable load pin. We will follow these steps to initialize MAX7219 LED controller. These are the exact steps to initialize LED controller IC. And finally, we will write values in data register. This will show character on LED matrix. We will see C code in next part of video.
Visit our website for more articles and tutorials. Visit us at www.embeddedcraft.org.
In this video tutorial we are talking about coding of MAX7219 LED display controller. This is the third and final part of our tutorial, SPI in Linux. You can watch the first and second part of that tutorial, link is given in description. In this tutorial, we will write C code to program MAX7219 IC. So, relax and watch this video till the end. Let us try ping with board. Board IP is 192.168.0.115. Wow, ping is happening. Now, we will establish SSH connection. User is pi, at the rate, board IP address. Enter password. Now we have logged into board. Just to verify, type uname-a. We are into Raspberry Pi. And pwd returns our current directory. We are all set to run our program now. Here is our C program. You can see activity of LED display in parallel. This is main function. We will explain this program little later. Let me first run this program to check if it works. Right-click, Debug Configuration. Our configuration name is LED Matrix 1. Project is LED Matrix, and we will execute program, LED Matrix 1, from debug folder. As you see, we set remote debugging. We have provided remote host IP address, username and password. And let us do debugging. You can see now, control is at the first line of main. Connection with remote host is established. We put a breakpoint at the end of program. Program will run till end of this line. Let us click on Resume button. Great, we have character A on the screen. It proved that our program is working. We have written some more code to clear LED display. Let us put a breakpoint at the end of main function. If we run till the end, now you can see that LED screen is cleared. Now, it's time to review our code. This is our main function. We have init SPI. Let us see what this function is doing. Entering into init SPI function. Here we are going to open SPI Device. This code is for initialization of SPI Device. Next, we are going to set SPI mode. IOCTL is the system call. Here we are going to set SPI mode. Here we are going to set the SPI speed. Next, we are preparing IOC transfer structure. This is data transfer speed. Data length. With this, initialization is complete. Next, we have to prepare our load pin. This is GPIO 25. Now we have to configure the LED controller. First, we have to turn on the LED controller. We need to prepare a 16-bit number, which is 0x0C and 0x01. This is shutdown register, address is C, and value written will be 1. We have written, write to SPI function. Going into this function. Here first we are making the load pin low. Preparing xbuff_tx, with the value, which we want to send to SPI. At last, calling IO control, with SPI IOC message, command. Making load pin high again. With this, we have, write to SPI, function ready. We will call this, when we need to send 16 bits over SPI. Now, we have to turn on LED controller. For this, we need to write, 1 to shutdown register. Next step is setting of displays rows and columns. For this we need to write, 7 into scan limit register. Next, we are setting intensity of LED display. We need to write, 0, to intensity register. Here we are configuring BCD mode. We need to write, 0, to decode mode register. Next, we are disabling test mode. We need to write, 0, to display test register. Now, we will write alphabet A on display. Now, we are ready to write into the data register. If you remember our font slide, we have values for data registers to display character A. We will write 0x70 into data register 1. We will write 0x88 into data register 2. And so on. Let us run this code step by step and review what will happen on LED display. We will start debugging. We have created separate video on the debugging of Linux application. You can refer video link in the description. Once debug context is set, we are on the first line of main. Stepping next. Setting GPIO number 25 as output. Power on LED controller. Setting rows and columns pixels. This is intensity control. BCD mode. Disabling test mode. Now, we are ready to write into data register. When we will write value in the registers, corresponding LEDs in the row will glow. We are writing to data register 1, we are writing 88, LEDs corresponding to row 1 is glowing. Same as, second row. Third row. Fourth, fifth, sixth, seventh, and 8. That's it. Now we are able to display character on LED matrix. We have written code to clear the LED matrix display. Let us continue debugging. We are writing 0 to row 1. This will clear row 1. Second row is going to be clear now. Third row. Fourth row. Fifth row. Sixth, seventh, and 8. And done. So, you have seen how to write character on LED matrix. With this we have completed our video tutorial series on SPI interface in Linux. Thanks for watching.
If you like our video, please don't forget to subscribe to the EmbeddedCraft YouTube channel. Visit our website for more articles and tutorials. We will meet in our next video tutorial. Meanwhile, goodbye and take care.